So as you heard, I don't know anything. I'm new here on campus, newer than you are, since most of you are, I think, are second year. I haven't even taught yet. I've just kind of arrived. So I'm a third-time emeritus professor. I'll teach a course in the spring, which is kind of my vision of the future of physics. So any of you that want to come, we'll talk about that there. I didn't follow the instructions making this, but I'm happy to talk about, I thought what the course was, and I'll give you my perspective on kind of the opportunities and what you have to do to make a career in physics for a little while, and then we can chat. I just made a few slides. I'm not an expert. We have no such course like this at Caltech. I don't know how students decide where they go, except from their thesis advisor, so that sounds like a great idea to have a course like this, but we don't do that. So that's just an excuse to say I have no experience in telling you any wisdom about it. But I will tell you a few things I understand about the numbers and the skills. First thing is that there's many, many opportunities if you have a physics degree, many more than almost any subject I can think about. Probably any subject that you take in college. It doesn't open as many broad range of possibilities as physics does. But in physics, we don't really teach or guide you for most of the things you might do with a physics degree. So much of the burden ends up being on you compared to, say, being a mechanical engineering student or a computer science student where you're tracked to a career that you've kind of picked in advance. Here, you may follow an academic career, like I said, but I'll show you the numbers, and most of you won't, just by the sheer numbers. So first, physics. Okay, we start in physics, as freshmen, taking just general physics and learning what physics is, and then eventually you get to be in graduate school, divided up into all these specialties. But then it doesn't map one-on-one into where people really do physics afterwards. So this is just a couple slides I picked off the web, but these are a variety of things where you find physicists who identify themselves as physicists, they belong to the American Physical Society, and yet what they do is everything from being a research scientist, is more like what you're doing now, to being a software engineer, doing engineering itself, even doing financial analysis. I've had quite a few students who have ended up on Wall Street, being, say, a high school teacher, or doing computing, or all these different things. So in physics, you've got, right now, you have to teach yourself to be a really great physicist. That's your job. But then you have to figure out how to go from here to there, and it's not a one-to-one map, which is really different than other fields, I think. And there's some numbers that reveal that you have to really think about this. So first, how is physics divided? It's something that maybe you all know, but roughly half of physicists are in one form or another in condensed matter physics. And in fact, this chart here is misleading in that there's other areas down here, like material science and applied physics, where much of it is in what we think of as condensed matter physics. So condensed matter physics turns out to be about half the number of physicists, half the number of graduate students, half the number of faculty, and so forth. So it basically divides that way. And condensed matter physics, for those who know it or don't, converge in this huge APS-run March meeting, which has somewhere between 10 and 20,000 people at the meeting, compared to, say, the biggest one in physics and astronomy is maybe 1,000 or 1,500, the April meeting. So condensed matter physics is really a big, big piece of it. I don't know, probably half you are in that area roughly. So that's the first thing. The second, if you look over on the right, the subject from my history and even today has been male dominated. So there's been, this is a graph of the number of females in the field, which is steadily growing, so we're doing better, but it's still 1 in 5 or something. So it's still, compared to biology or other scientific fields, we don't do very well yet, but we're working hard at it. It's a difficult problem because we lose them at much younger age. It's not really that at the college level we're losing the potential of having more females in physics. We are losing them in the educational system on the way. It's a complicated problem, but we're doing better. Also, it's basically a white sport, unfortunately. So we're not doing very well with ethnic and race minorities, which is evident here. And also what's evident to me here is the people who do the statistics probably aren't always very good, because I just don't believe that the Asian Americans only represent 2% of physics. It's just not true. And so you have to sometimes take some of these studies with a little bit of a grain of salt. That's Asian Americans, not Asians. But I think we know it's bigger than that. So that's more or less the group of who we are. There's an interesting question that I found when I was preparing this that was asked by the American Institute of Physics to people when they were surveying them about whether they would do it again. And I found that interesting. So this is, 5 or 10 years later, because they're surveying what people are doing now compared to what they did, and whether they would do it again. And they asked first U.S. citizens, which are about half the PhD degrees in the in America, and half of them are non-U.S. You'll notice that 73% after 5 or 10 years say they would do it again. They would go to graduate school in physics and get a PhD. For some reason, it's only 50% for non-U.S., which is kind of interesting. And there's a small number that think they might have picked a different institution to work in, or a different subject. But I think overall, physicists are not afterwards reflecting back that they should have studied something else. In general, the majority seem to feel that was a good thing to do for whatever's happened to them career-wise afterwards. I can't give this talk without talking about salary, so you know what you're going to make depending on what choice you make. So the choice isn't just where you want to spend your energy and time, but what paycheck you want to take home, and that really is quite different depending on what you do. If you look on the right here, if you can read it, the private sector is about twice the starting salary of those of you that choose to stay in universities, get a postdoc, or go to a laboratory, all of those. So basically, the choice of going in the private sector is financially one that you are aware of, but it's clearly in a real survey a clear factor of 2. And I also looked up the Bureau of Labor Statistics, which is the most reliable way you can look at any field to see, or any subject matter to see what the average salaries are, because people report they use IRS statistics. And so the average pay of a physicist and astronomer in the US in 2017 was $117,000. And the total number, interesting, that identify themselves as physicists are 20,000, which is about 40% of the membership of the APS, which is an interesting thing. This is an important subject because if you look at the Bureau of Labor Statistics, they're pretty good at seeing trends and so forth, whether the jobs are going to change. Of course, there can always be a recession or something that changes, but basically they judge this field as one that'll grow at a 14% rate, which is considerably faster than the average in the coming years. So however they do it, that's the Bureau of Labor Statistics. And lastly, at the beginning, and then I'm going to be more specific, at who hires PhDs in physics. And if you look at this, so this is a breakdown of where the jobs are for people that get what you're going to get soon, a PhD in physics. And if you look at the section here, to be pure physics, that means to try to be what I am or he is, a faculty member in a, say, research university. There's also educational, doing education, but maybe teaching. and other educational areas, STEM areas, or areas that aren't purely physics, but maybe they make you coach the football team or something. And so altogether, it's about 30 or 40% of the total. I'll show you why in a little bit later, but that means that roughly 2/3 of you are not going to be doing what we're doing. You're not going to be in a research university. And those of you that are, I'm happy to tell you I'm pretty much of an expert. We can talk about what kind of careers there are there. The rest of it is really what most of you are going to be doing, and I think, unfortunately, we're not very good at helping you with that, and so you've got to do a lot of work on your own. But there are mechanisms. I mean, as I look, the AIP is a good source of doing kind of surveys. The American Physical Society, I'll show you, has a whole program that involves kind of showing you what the opportunities are. And I think the main message I have for you today is this is one area where you can't rely so much on faculty or just a course like this, but you've got to kind of realize that with the broad skills you have as a physicist, you should really try to understand what it would mean to become a computer, deep learning person in computing instead of this, or in medical physics, or work as an engineer. Or, of course, the easiest one to conceive of is to become an academic person, but only 1/3 of you will end up doing that, I think. Okay, now let me become a little more personal. That was kind of just survey-ish. And what I'm going to do is just very, very briefly go through what I do, but from the perspective of what I know about what that means for what students that have worked with me and people have done. And then at the end, I want to make some more general comments. And I need some interaction, so I'm going to talk for another 10 minutes maybe. And in terms of a real research talk, I'm going to give a colloquium by the spring. I'm going to teach a course in the spring, so I'm not really going to try to talk very much about physics now, but just a little bit. So first, I'm an experimental physicist. The opportunities in experimental physics versus theoretical physics is, I think, job-wise, much broader. So an experimental physicist has many, many skills that can be used in areas beyond what they did as a graduate student. So in general, those of you that are in theory have even more of a challenge, and you better work at it, because you're not all going to become professors in a research university. And those of you that are in experiment, realize what skills you develop, because it'll determine and can determine what kind of areas you're able to go into. So anyway, I'm an experimentalist. I've worked in particle physics. I've worked on particle accelerators. That's what I want to emphasize today. They're all different in terms of kind of technologies and so forth. And as was mentioned at the beginning, my main activity in the last decade or two and now is gravitational waves. So let me just say just a few words, but not from the perspective of the discovery as much as what's there. So the gravitational waves were first predicted 100 years ago by Einstein. They couldn't be detected. He thought they wouldn't be detected. And the only reason why it's taken 100 years, the main reason, is not because we don't have any cleverness or ability to do experiment, but because the technologies really weren't there to do gravitational wave measurements. And we've only developed those in the last couple decades. And that required high-power lasers and other techniques that basically I won't go through in detail today, but are very, very state-of-the-art or beyond the state-of-the-art. Gravitational waves are a prediction that I just show here, come from the fact that if you study general relativity and you set up the problem of general relativity, it has an equation. I've given the details here if any of you actually know general relativity of what I assumed in terms of a metric and so forth. But then you get something that looks very much like the wave equation that you have in electromagnetism. And the wave equation has in it this term h mu nu here instead of for gravitation, in contrast to electromagnetism. but otherwise it's the wave equation. And this h mu nu is actually what's called the strain in general relativity, and it's what we measure in the gravitational wave experiments. So and this equation, of course, gives basically plane waves. And just like in electromagnetism, there's two polarizations of the plane waves. The two polarizations in this case, by the way, we haven't seen this, but we infer it. There's two polarizations of the plane waves, but you'll notice in the drawing here, they're at 45 degrees to each other instead of 90 degrees to each other. That's a reflection of the fact that gravity is spin 2, while electromagnetism is spin 1. So basically that's the idea. Took 100 years, and then developing a instrument, which I'll just show you a picture of, we were able to see two binary objects which are locked to each other like the moon around the Earth. In this case, two black holes. They're each spinning, and they're going around each other. As they go around each other, by general relativity, they radiate away some energy, and so they slowly come together. The energy they're radiating away is what I just showed you. It's in the form of gravitational radiation or gravitational waves. And depending on the details of how much what the masses of these are and the frequency this is going around, the signal it has different frequencies and different sizes. So two light objects will have a much longer path of coming together. This is getting closer and closer together and more energy emitted, and the heavier ones not quite so much. And this is what we've observed. And as I say, I'll give a seminar on this at a colloquium on this next spring. The only thing I want to say is it's hard because that little h that I showed here that we've measured is an incredibly small number. It's 10 to the minus 21. And that translates to having to measure a warpage of space-time of that amount. And we do that by having a detector that's capable of measuring this. But if I made say a circle of free masses and a gravitational wave came through, it would distort that circle by 1 part in 10 to the 21. So that means if this is a meter, it would only be 10 to the minus 21 meters that you can measure. That's a pretty small number. In order to make it larger, we developed a way to make detectors that were large. So they're kilometer scale, which makes the problem still incredibly hard. It's 10 to the minus 18 meters instead of 10 to the minus 21. And a proton is 10 to the minus 15 meters. So it's 1/1000th the size of a proton is this warpage of space-time that you have to be able to detect. And that's why it took so long. We did it in 2 interferometers that I'll talk about in a separate colloquium. But the length of these is kilometers. This is 4 kilometers long. We have 2 of them, one in the state of Louisiana and one of them in Hanford, Washington. They detected identical signals, but at slightly different times. And by the time difference between the 2 and the phase difference, we can infer where it came from, can determine where it came from. This is the very first detection, the one that we measured and drawn. You'll see it looks like the little sketch that I gave. When it enters our detector, we start getting a small oscillations, then they get bigger and bigger as this merges together. Then finally it merges together and afterwards settles down a little bit. Shown, first thing to notice is they look identical. They're actually shifted by 6.5 milliseconds. But the other thing is there's a little white line drawn through it. And the little white line, which you can barely see it because it looks like the data, is the calculations of Einstein's general relativity for 2 massive black holes merging like this. And this is the picture that was figure 1 of our discovery paper and was all around the world and basically resulted in a Nobel Prize. These are my 2 colleagues, by the way, Kip Thorne at Caltech and Ray Weiss at MIT. We've worked together for 25 years on this problem. Okay, and just to illustrate, this is going to open up lots of other ways that gravitational waves can be detected. So far we've had a lot of graduate students that worked on this problem. What are they doing with themselves? Quite a few actually have gotten academic jobs, much more than 1/3, I'd say. Why? Because the choice of subjects, luckily, is one that has excited physics in general. I mean, I got a prize, but it's excited physics, and physics departments, when they decide they want to add new faculty, are often attracted to an area that they think is emerging or doing well. So probably more than half of our equivalent to you guys, PhDs that have worked with us, but certainly not all, have made academic careers, gotten professorships and so forth. So one lesson there is, work on something that people like and want to do, and you have a better chance of an academic job. The ones that didn't were often by choice. So for example, I've had 3 students, I'll mention, that over the last 10 years or so, that have gone on to pretty good careers outside of working in a very exciting research field and being in a university by their choice. One is at SpaceX, and he was responsible for a lot of very precise, almost, if it's not a dirty word, engineering that we did in putting together the mirrors that are used in an interferometer in a very precise way, which I'm not going to describe now. He went on to SpaceX. He's in charge of quite a large division of SpaceX, which is in Torrance, and he made, I would say, a career where he started in physics and did physics, is doing essentially the same thing, relabeled as kind of a chief engineer of a very large and forefront project in engineering, which is satellites and space program. The second one that worked for me, this is more recent, I got interested in the problem of how do you look for gravitational wave sources that we don't anticipate because they aren't seen in regular telescopes, but may give a signal in gravitation. So to do that, how do you look for signals that you don't know what you're looking for? The way we went about it was to develop a way to look for as kind of generic looking waveform as we could put together. And I had a student that developed the waveform that we use, which was based on a wavelet techniques. Wavelets is a good way to make a kind of generalized waveform. But no matter how you do that, it still has assumptions built into it. So he developed the wavelet technology. We knew it was limited. And during that period, we decided that probably the way to really learn, to really search, the best is to use the data that we have and use deep learning techniques to look in a more unbiased way at finding anything that's completely different from all the data that we take otherwise. And so he became, as physicists do, pretty much he was already an expert on things like wavelets and stuff, on deep learning. And he could have easily gotten a degree, when he got his degree, a job in a university in computer science or in physics. He went to Google. He's making a lot of money. And they're very interested, of course, in deep learning. So that's 2 different ways that people have used the physics degree to do pretty exciting things without just an academic career, which is part of my message here. This one is only to illustrate that we picked this. This is what we've seen. There's all kinds of other sources of gravitational waves that we expect and the ones that we don't expect that'll make this field flourish in the coming years, depending on whether we can make better instruments that we already did and realize we worked pretty hard to get to where we are now, but we're working very hard to try to do yet better, more sensitive instruments that can see effects that are smaller than big black holes colliding. Second subject. So the second subject that I've worked on in some detail is particle accelerators. This started when I was undergraduate. When I was an undergraduate in Berkeley, my academic advisor was somebody named Owen Chamberlain. Does anybody know who he was? He won the Nobel Prize for discovering the antiproton, which was discovered in Berkeley more than 50 years ago. He was my undergraduate advisor, and the reason that he was the reason why I switched, I started in university in my freshman year as an engineering student, but I had to take freshman physics, and then I switched into physics because they were discovering these particles. It was all much more exciting to me, even though I liked engineering than engineering. So I didn't know what happens when you make a discovery like this. I know now. Everybody's in your face all the time. And so I was his undergraduate advisor, and he was working up on the radiation laboratory, which is above the campus in Berkeley. And it's quite a steep hill. And now they have a nice little shuttle bus that goes back and forth. But in those days, you either hitchhiked up or walked up the hill. And of course, there's an overhead in doing all that. And I would get up to the hill as an undergraduate to do research, supposedly, having signed up for research units, and he was too busy to see me, typically. And so I wandered around the lab because I wasn't just going to turn around and go back down. And I found a friendly face in the 184-inch cyclotron, the kind of famous machine that was there from just after World War II. And that ran the machine. And so I learned about machines by spending my time by default at the 184-inch cyclotron, because Owen Chamberlain was a nice person to have as an advisor. It stimulated me, but he wasn't available. So I started learning about accelerators, and I've worked on accelerators in addition to doing physics ever since. Have had several students that got PhDs on accelerator physics. So this is a different subject. So what is accelerator physics? Building accelerators, there's these big accelerators. The physics itself is easier than, say, particle physics. Particle physics is, or gravitational waves. Gravitational waves, you have to understand general relativity. That's not too easy. To understand particle physics, you really need to, if you want to understand the physics, you need to understand quantum field theory. That's not so easy either. To understand particle accelerators, you have to understand basically Jackson electrodynamics, or a graduate course in electrodynamics, the Jackson textbook, with one added feature, and that is that Jackson's course doesn't treat nonlinearities. So accelerators are basically Jackson plus nonlinearities. And that's interesting. You can do most of that or simulate it. And so accelerators are something you can really understand at a fundamental level, and then you have to implement them. And it's always appealed to me for that reason. In the meantime, a lot of technologies have been developed. We're in a situation now where we've gone through 3 generations of pursuing particle physics by having colliding beams of protons on protons or electrons on positrons, and in fact have used both. So we've used at the same energy both probes until now. So we've done that from the 1960s, the first ones, and the next generation at higher energy, and the next generation. And now we've built a big machine, which you all know about, which is at CERN, called the LHC, which is the Large Hadron Collider. But we don't have the electron machine to go with it. So for example, the one discovery that's been made so far at the Large Hadron Collider is the discovery of the Higgs boson. That's a fantastic discovery because it has to do with us explaining something that everything we know about particle physics didn't explain, and that is, where does mass come from? And it's even broader than that because it tells us something about the whole, what the vacuum is and how mass exists in the universe and so forth. So it's an important concept. And the particle itself is rather unique. It has zero spin. It weighs a mass that we aren't able to predict. And maybe or maybe not, it has the features of the simplest picture of the Higgs that was proposed in the 1960s by Peter Higgs, or alternates, which people talk about. To determine that, you have to make much more precise measurements. And that's hard to do when you scatter protons on protons, because they're such complex objects. Each proton is full of quarks and gluons, and they scatter off each other, but you don't know who hit who with what. And electrons are simple point-like particles. It's harder to make the machine, but when they scatter off each other, you understand the initial state very well. They're point-like particles that annihilate, and you know the quantum numbers, and you know all the energy goes into a final state energy. So we've made an electron machine to go with the positron machine for 50 years, 3 generations. And this new generation, we would like to produce an electron-positron machine now as the next particle accelerator that would complement the Large Hadron Collider at CERN. To do that, we have to develop a new technology. And the reason is that electrons, in contrast to protons, are so light that when they go around in an accelerator, go around in a circle, they radiate away a lot of energy, unless the circle is the curvature is very shallow. But you don't want to make something too big, it's too expensive. So we're in the regime now where, in order to reach the kind of energies that would produce the Higgs boson, it's not economical to make a large circular machine. So therefore, you'd like a machine that doesn't go around in circles, and that's a linear machine, just 2 accelerated beams that hit each other. Of course, that's hard. It's like taking 2 rifles and shooting bullets at each other. We have to make them have a high probability of collision. They have to be very accurately positioned. And to do that, a lot of technology needed to be developed. So there was a design team put together to do that. I led the design team from 2005 to 2013, where we designed this linear accelerator and all the elements around it. And that machine is now in the Japanese government highest levels to decide. So sometime in the next 6 months, there'll be a decision, plus or minus. It's a political and financial decision. The design is finished. So, but now for today's thing, how is this different than the gravitational waves? First, no one's going to buy a large interferometer like we made in gravitational waves, so it doesn't have any commercial interest at all. However, particle accelerators have a lot of commercial value. So particle accelerators are a $10 billion, which is pretty big. It's about the size of the movie industry. Industry in the world. They're used for making pharmaceuticals, they're used for medical purposes, they're used for material science, they're used for many, many things. They're developed primarily, because that's where we push the technology the most, for particle physics. And that feeds all this other. But it means that students who have worked in this area, and it's just to illustrate, have a skill that is immediately enables them to get very even better jobs than the SpaceX job I talked about, because the idea that you can use a linear accelerator, for example, to make one like we developed these cavities, to make pharmaceuticals means you can make pharmaceuticals in a much more compact device in the basement of a hospital. The one problem of making certain chemical pharmaceuticals is transporting them, keeping them alive long enough. So having the ability to make them locally is a big demand. And so there's a lot of industry that want the expertise and the leadership to do this. So I had several students and young postdocs that have moved on into what I would call medical industry in applying accelerators and accelerator physics to what they knew about it to a job. So it's another illustration from my personal experience. That's just showing the fourth. The last one, which I'll mention, is newer for me. I've been kind of running the oversight, technical oversight committee for the next big astronomy project, a survey instrument, an instrument that will survey the sky, made with a really sophisticated camera. The camera is very, very high tech. And this is being built now. They've made much of the apparatus, but it's being put together. It's supposed to start taking data in 2022. And at that point, it'll survey the same part of the sky. This is the sky. Same part of the sky where the color here represents how many times over 10 years that part of the sky will be seen. So this will be seen, 1,000 times over that time. During the reputed times, you can see any transits change or any issues change. My interest in it has to do with a phenomenon in physics or particle physics called dark energy survey, but this is a much more broad instrument for astronomy. And again, where students and postdocs and people working on it have moved into other areas, which is today's subject, is a very growing field. And in fact, there's an effort here that is being built up or has been built up in handling large data, big data. So this is one of the biggest producers, will be, of data in the world. And so they've developed a lot of technology and abilities and ways to approach handling large data and distributing data around the world. So the people working there and postdoc that's worked with me have moved into working on large data. So it's another example of just kind of doing almost the most fundamental research, which is what I do, where people have moved into other areas. So I said all this already, I think. So a few more comments, and then maybe we can just chat. These are numbers that, to me, tell you what the raw truth is. This comes from the AIP, the American Institute of Physics. You can go on the web and look at it just as I did. This first one is the number of PhD degrees that we have. So presently, this is earlier than now, and it's grown. So it takes a while for them to get the data. So this is 2012, and it's not lower now. We produce about 1,800 PhDs in physics in the US each year. So that's the first number. The number of faculty positions in PhD granting departments is only about 150 a year. So we're producing 1,800 for 150 faculty positions, which really tells you that there's not that many positions available. If you add the positions that are in minority departments and bachelor granting and not research institutions, it gets up to maybe 200 or 300, but that's still much smaller than 1,800. Now the 1,800 can be halved maybe, because, but not really, but about half of the PhDs in the US are non-US citizens. And a lot of those go back to their countries, so I don't know how much to degrade it, but somewhere between 900 and 1,800 PhDs are produced a year that want a job in the US. And the number that can work in universities and any sort of teaching is about a third of that or less. So that tells you that there's just a numbers issue. It's of course better in some fields, worse in other fields, and so forth. It's not uniform, but you can see the numbers. The second is this, if I can read it. This is how the careers spread out then in physics. This is the one I looked at, academia, so it's about a third of the area you see here. Most go into industry, physicists. This is from the AIP studies. And some go into government labs, and some into non-STEM work, something that isn't science. So again, you see the academic part represents maybe a third or quarter or something of the total. Second interesting fact, I think, is that you make a decision when you get a PhD. You're going to try to do it in a university or go to a government lab or go to industry. how much movement is there after this? And this is, again, the mobility from an AIP study. And this looked at people who got degrees quite a while ago, 1996 to 2001, and then what they're doing now. And so at the beginning, they were divided up like this. Again, academics was maybe a quarter, a third of it. And industries here and government jobs are here. And this is the changes as it went. Very little, these little stripes and stuff are the fact that the number of jobs in academia went down a little bit, and the number, it's harder to get a permanent job in academia. But there's, as you see, there's not a huge movement from one to the other. So the message that I take, if I believe this, and I do, is that the initial decision you make when you graduate, what you're going to do, isn't like, well, I'm going to say oops later. It's not. It gets harder and harder to change if you go into these big sectors. It's easy to change what you do within industry or what field you work on in academia. I mean, I worked in particle physics, now I do gravity or something, so that's easy. But I changed from one university to another. But in terms of changing from an academic career to an industrial career, the time when that's done is pretty much when people get a PhD, and the numbers are what I showed you. So lastly, I want to say there's a lot of resources. And so I think the problem, as I said, for a lot of you is you're going to go into something that we don't know very well, except to look at numbers like this, and you have to do some of the work yourself. That's recognized in the community. In the American Physical Society, they actually have continuing set of webinars where they discuss different subjects. I just picked this off their webpage just to give you an idea. So this is March a year ago, and it was what you can do with your degree in different ways, people talking about it. And this one has to do with, becoming an entrepreneur. And they're just right on the website, and you just have to turn on and take part in it. So if I were one of you, I would be sobered by the message that you have to do some work on your own, but you're supposed to be good at that anyway. Being physics students, you have the wonderful thing that your skills are very broad, so there's a lot of different opportunities. But the job is your own to kind of figure out what you're going to do. It doesn't affect what you do while you're here, but what you're going to do when you leave, I think. And those of us that have goodwill can try to help, but we're not experts at it. So I think that's as much as I want to say, and we can chat the few minutes that are left.
Thank you. Questions?
Don't be shy.
Yeah, don't be shy. This is your chance. Yeah.
Could you clarify a bit more how you made your decisions for your career path?
I was blind to it all. I was naive. I followed my romantic dreams, and as I mentioned, of doing particle physics and making discoveries, and luckily things worked out for me. But I think it's not a path that I would recommend at this time in the future. So I didn't really grapple with it. I just kind of did what I wanted to do. And luckily, it worked out. Yeah, hi.
Did you ever have like a project or something that you were working on that just failed miserably and you had to recover from it, or that made you question your direction?
No, I've had a lot of failures, but not anything that made me change directions. In fact, I think experimental physics, one of the great attractions, you don't make discoveries very often. I mean, I've worked in gravitational waves for 25 years, and people often ask me how I could stay with it that long. And it's really all the things that we built or tried that didn't work, and the fun of figuring out why it didn't work and making something make it work. In that case, we knew we weren't limited by nature itself, just our own creativity and technical ability to make things. And you have an idea, you try it, it doesn't work. That's the fun of doing physics, kind of. If everything worked, you're being far too conservative in what you're doing.
So how did you, in those cases, I mean, in that 20 years when it wasn't working, how did you keep the funding going? How did you keep people convinced that you should keep
we didn't overpromise, and we made progress. So it doesn't mean everything we tried worked. It's just that it's a little of this and this and this, and you're climbing a mountain where there's dips and so forth. But there's a lot of failures on the way, but the failures are almost more fun than the successes. Anybody else? There were some other hands. Yeah.
What led you to switch from particle physics to gravitational wave?
I still do particle physics. I'm opportunistic, I guess. I have broad interests, and if I see, and I want to do science, and if I see a way to do it, I am not afraid to do something different than I did before. So it wasn't a hard decision. If you have the chance to measure gravitational waves, it's a great thing to do. And at the point when I changed, I thought, I assessed it and thought that we could do it. I thought it would happen much faster than it did, but eventually it worked.
Other questions?
Yeah.
How much of your time was spent doing the accelerator stuff versus the general gravitational waves? So how do you
Yeah,
spend
yeah. It turns out that we did a really major upgrade to the gravitational wave experiment between 2007 and 2013. And we did the work, the design of it earlier. Then we had to wait in line for money from the NSF. All of this happened during that kind of interim period between when we finished with the initial version of LIGO, designed the next one, and we started building it. By the time we finished the linear collider design, we were ready to start putting together. So it all worked. The timing for me fortuitously worked out very well.
I assume that a lot of your work you do is writing grants and
No.
or no? Are you still involved directly in the science more? Or?
Yeah, well, if you do these kind of things that I talk about, they're pretty big, and so the grants are hard to get, but they're big, and you don't have to write them as often. So biologists are writing grants, or even condensed matter physicists, I think, are writing grants all the time. But one of the advantages of bigger science is the grants that you do write are reviewed to death, and you're criticized. But once you get funded, it's you're reviewed and criticized, but you're not writing grants. So I don't spend that much time writing grants.
So most of your time is actually looking at data or?
Well, right now for us, I think my time is on the instrument itself, because what limits us. The data is more fun, like trying to use deep learning to find is great fun, and I'm doing that. But for us, what's going to limit and determine how much we can do in the next decade or something is how much we can improve the instrument. And I have a lot of history with the instrument, so I have a lot of stake in what can be done and can't be done. So basically trying to improve. We've worked very hard to make it this good, so making it better is not easy, but it's the my main emphasis. That's another point, is that I think that students can grow in two different ways, and I don't think I have my own bias, and that is, say you work on something like this that has many aspects, everything from making fancy lasers to doing deep learning. Okay, so what is a student better off, becoming an expert at deep learning, or trying to do a breadth of things? And I think it's very much an individual decision, and I don't think it limits so some students get a PhD and they really got to be good at something, and maybe that determines their career. Other ones maybe took a little bit more a broader view, and I think different strokes for different folks, kind of. I think you can do it either way.